My name is Michael. I'm the primary maintainer of grpc for node.js. Today, that's what I'm going to be talking about. This presentation takes about 20 to 25 minutes, and then I'll take questions at the end. So first, I'll talk about grpc in general, for those who are unaware. In some ways, it's similar to REST. It's an RPC system. In this case, it works on top of HTTP2, which gives us some advantages. It enables streaming RPCs, and you can multiplex concurrent streams within a single connection. The grpc libraries that we provide exist in a variety of languages with compatibility between them and backwards compatibility. And they have additional rich features, including authentication and protocol typing, primarily using protobuf, though other serialization formats are usable too, and a variety of other rich features that we've developed over time. So if you're using grpc, the primary development workflow is to write a .proto file, or whatever IDL you use, and then to generate client classes and service definitions using a tool, and then write either the code that uses the client class or the handler code for those generated service definitions. In Node in particular, we provide tools that support two different workflows. One is to precompile the protobuf code into those generated things using Proto-C, which is a Google library. And the other is to parse the proto files and generate that code at runtime using a different library that we provide that's built on top of the third-party protobuf.js library. And then I'm actually going to jump into a quick demo of what that looks like in practice. So this is a variant of our Hello World example. As you can see, this is a Proto-3 package that defines a package named Hello World with a service that defines a single RPC method. In this case, it's unary because neither one says it uses a stream. And then we define the message types here. So then if we look at the client code, this is all it takes to spin up and use a client using that runtime code generation that I mentioned. So the code up here above this line is all loading the file and extracting the package object. This looks like quite a bit, but it's all kind of standardized. You can easily factor this out. And then we simply instantiate the client class with the target address and insecure credentials because we're not using TLS in this case. And then we call the method using the types specified before. So if we look back at the proto file, you can see that the name is a string. So we pass an object with a name that is a string. And then we get a callback that shows the response. And then if we look at the server, you can see that there's the same loading code at the top, and then we just define the handler for that method. We create a server object, add the service using the generated service definition loaded above, with indicating that this is an implementation of that method, and then we simply bind to a port and start. And then if I go over to a terminal, We just npm install like usual. It's very normal npm installation. One thing I want to point out that that I'll get back to later is that we install this binary that, as you can see, has a few different parameters that define it. And then we simply run the server, and then we run the client. And you can see that it outputs the response that was defined. So going back to the presentation. Now I want to talk a little more about the one dimension of the architecture of this library. So there's three main components. There's the C core, which is written in C and increasingly in C++, that really implements the full gRPC protocol and actually the HTTP2 protocol. It directly uses TCP. And this library is shared among several of our other, this core is shared among several of our other libraries, including Ruby, Python, and others. And we've done some work to have it interface with the libuv event loop, which is what's used within Node itself. And then on top of that, there's the native add-on code. This is a Node-specific concept. It uses C++ APIs provided by the Node runtime to define JavaScript APIs. In this case, the primary purpose of our native add-on code is to transform types and control flow between what's defined within the core and what's useful in a JavaScript API. And it provides a callback-based interface. And then finally, there's a JavaScript surface layer, which is JavaScript code that consumes the API of this native add-on and exposes the final public API that the library has. And then I want to talk a little more specifically about the precompiled binaries. You saw one downloaded in the line I highlighted. So the core and the native add-on code are statically linked together into a single binary file. And we distribute these. We use a library that's called Node Prejip, which is built for this purpose. It's responsible for both downloading the appropriate binary for the current system and for loading it at runtime. And it falls back to compilation, which we hopefully have to deal with less and less frequently. We distribute these binaries using Google Cloud Storage, all in a single bucket. And there's a lot of different factors that affect the binaries that we have to compile different binaries for. Node versus Electron, different versions of each. Different operating systems need different binaries, different architectures. And then we have a set of custom scripts and some internal CI jobs that generate this for every version of gRPC that we publish. So that brings us to issues that we've encountered over time, primarily as a result of the existence of this native add-on and this distribution system. So installation becomes more failure prone. Since we're distributing these using our own server, we have it's an extra point where downloads can fail. A user that can access NPM servers just fine may start experiencing failures if they cannot access Google Cloud Storage. as some of our users in China experienced at some points. There's also, sometimes file system access failures. Node pregip touches the file system in its own way, and sometimes, especially in certain Docker environments, it's not properly set up to handle that. Every time there's a new version of Node, we have to proactively publish these new binaries, in order to support it. And whenever there's a delay, people start experiencing failures. And similarly, if they're installing an old version of our library that doesn't support those versions, they experience similar failures. And as I mentioned, there is a fallback, but a lot of environments like Docker and even regular development environments for Node don't have the tools available to actually compile this code. So the fallback doesn't work either, and they just completely fail. Besides that, there's people also have trouble loading it even once they successfully installed the library. This particularly happens if you install on one system and then try to deploy your library to Docker or to some cloud environment, because the detected version at installation time doesn't match the needed version at runtime. And debugging was another big issue. Native add-ons are very opaque to Node developers when they're trying to debug code. You can do a Node debug session, and then you just get no introspection into anything that the native add-on is doing. And finally, I mentioned that we have these variety of factors that impact the binary. This has led to this combinatorial explosion. We don't support every single combination of these things. Some of them just don't make sense. But we still have well over 300 binaries that we publish with every single version of gRPC. That total almost half a gigabyte. So as a result of this, the solution that we came up with was to re-implement gRPC purely in JavaScript on top of Node built-in APIs. So the library itself is written in TypeScript. That's become a lot bigger in the time since we started this project originally. And we used the built-in HTTP2 module in Node, which was introduced fairly recently. And this was fundamentally important to this project. HTTP2 is a complicated protocol, and re-implementing all of that or using some third-party library that we don't necessarily know much about was just not worth it. Wouldn't have worked well. So this is an ongoing project. We currently have a client with the basic functionality to make basic requests. And as I mentioned, cancellation and deadlines and automatic reconnection are all supported. And so when we were designing this new implementation of the library, our primary design consideration was API compatibility. We want to make sure that to the greatest extent possible, this new implementation is a drop-in replacement for the old one. We couldn't do that perfectly. Some of the APIs from the original library are deprecated or otherwise could not be implemented with this new implementation. So those are omitted. But every single API that this new library does provide exactly matches what is provided in the original. And we prioritize the client and the basic functionality because the demand for this library primarily came from people who wanted to distribute client libraries that maybe use some generated code and depend on gRPC. And all of those libraries were experiencing the same friction that I described with their own users. And so this was kind of the biggest place where we could gain from providing this new implementation. And we've decided so far to omit some advanced features that we are completely unaware of any demand for, kind of simply as a prioritization thing. So, certain advanced client-side load balancing features, whole stream compression, some others we'll simply omit for now. And then I have another short demo to show what I'm talking about. So if we look back at this client code again, to show this API compatibility, I can simply replace the required gRPC with the new library, and then just to show that we're actually affecting this file, change that to, and then if I go back here and I run the client code again, you see it has the new response. So this is using the new library. No other code had to be changed to make it work, and it's completely compatible at a protocol level. And so finally, in the future, our next development plans for this library, we do want to add a server. That's a big priority. We want to add simple client-side load balancing support. This is if a DNS server returns multiple addresses for a single name, we can balance requests between those backends. And also TypeScript, as I mentioned, has become a lot bigger in the time since we started this project. And the code that gets generated, we don't generate TypeScript signatures for it, and that's kind of our users' biggest gap when they're trying to use TypeScript with the library. And so this doesn't have to be exhaustive. As we learn about what features developers who use gRPC really need, we can use that to determine which we have to focus on when re-implementing things. So if you use this library or you're interested in it, I encourage you to check it out, and in particular to tell us about what features you need for your own use cases so that we can better prioritize our own development. And that's actually all I have. If you want more information about gRPC in general, you can visit our website at grpc.io. And if you're interested in this project in particular, we have a gRPC node GitHub repository with these different libraries. So with that, are there any questions?
So are there any good educational materials on how to actually deploy gRPC-based application or Kubernetes? How neutral man? I'm not aware of. Hold on. Do you want to repeat the question?
Sorry. He asked if there are educational materials related to deploying gRPC on Kubernetes in a cloud-neutral manner. I'm not aware of that in particular, but there are a lot of resources on our website. There might be something there. So we do support providing client certificates to implement mutual TLS auth. We don't have necessarily advanced features like refreshing certificates, but the basic ability to provide a client-side certificate is there.
How does the performance of the new library versus the old one compare?
So in our initial tests, so we've initially done some latency tests, and so far the original library has about half the latency of a full request response, but it's a lot more optimized. So in the long run, I expect that comparison to change over time. Back pressure. This is mainly possible in the streaming case. We provide an interface that uses Node's own stream classes, and if you stop reading on a stream, then after the buffer fills up, that will eventually push back to back pressure on the server.
Can the TypeScript client talk to Unix sockets?
The TypeScript client currently does not have support for Unix sockets, but knowing that that's something people care about means that we'll have it on our roadmap.
How does this compare to like grpc web? Is there any kind of like integration with the
We currently don't have direct integration there. grpc web uses its own protocol and currently uses proxies to communicate with other grpc servers. So our current plan is to support both of those going forward. Once we reach feature parity, that'll be a point where we reevaluate that depending on actual usage that we see.
What's the schedule for the server project?
I don't have anything specific that I can give you. I'd say we're definitely targeting, probably the next couple of months. Right. So sorry. He asked about the schedule for adding a server to the grpc-js implementation. That could definitely be something that we would look at in the future. We're focusing more on features than performance at the moment. But yeah, I can see WebAssembly being something that we would look at in the future. Currently, there are some fundamental challenges with getting something like this web packable. The primary issue is that current browser HTTP2 libraries or implementations don't actually fully support certain parts of the HTTP2 protocol that we need. And so the APIs that they provide also don't provide that stuff. So There would really have to be some fundamental changes in a couple of places for that to become even possible. Once that is possible, probably somebody will write a shim between the HTTP2 API provided by Node and probably the fetch API provided by browsers. And once that happens, it should be completely webpackable.
Does the static generation of the code, will that use Proto-C, the Proto-C binary?
Yes, it does. We provide a plugin on top of Proto-C that generates service definitions that use the types generated by Proto-C in its normal JavaScript generation mode.